Welcome to Pre-Calculus. Today we will investigate representing geometric sequences using both explicit and recursive equations. We'll take a look at 4 examples total, and then we'll use our equations to find some term in each geometric sequence. Our first example is this geometric sequence 4, 8, 16, 32. And we want to begin by writing an explicit equation to describe the sequence. Now, different from arithmetic sequences, a geometric sequence goes from term to term not by adding a common difference, but by multiplying by a common ratio. So similar to what we did when we were writing explicit formula for arithmetic sequences, I want to start here by deciding what's the common ratio. To do so, I just take each two terms and I divide the second by the first. In this case, 8 divided by 4 would give me a ratio of 2. I want to check to see if that's common. 16 divided by 8 is also 2, and then 32 divided by 16 is also 2. So it is common to each of the terms as we go in this sequence. I'm going to identify that as my R value. My common ratio is 2. I also need to find my first term. My first term here, a sub 1, is going to be 4. Once I have those two pieces, I really just need to grab my template for the explicit formula for a geometric sequence. And that explicit formula template, specifically again for geometric sequences, would have this form. It would tell me that the nth term, a sub n, is equal to my first term, a sub 1, times the growth rate, that common ratio, to the power of n minus 1. So for me to write an explicit equation to represent this geometric sequence, I just need to substitute a sub 1 and r. So we'll do that. A sub 1 again is 4, that's my first term. My base, the common ratio of growth, is 2. And then I just need to fit in the power of n minus 1. And that gives me my explicit formula. Now, I also want to calculate the 11th term. I have this instruction here, find a sub 11. So just like we did with our arithmetic sequences, I can use this explicit formula to find that directly. So a sub 11 is going to be equal to 4. I'm just using my explicit formula here, times base 2 to the power of 11 minus 1. I can reduce that down to 4 times 2 to the power of 10. And that's a lot to multiply, so I'm going to take that to a calculator and evaluate. 4 times 2 to the power of 10. So we'll type into Desmos here, 4 times 2 to the power of 10. And immediately we get a value here of 4,096. We'll head back to our notes screen to finalize that product. A sub 11 is going to be 4,096. So it does highlight the value of the explicit formula. It makes calculating those large numbers quick. Let's take a look at a second example that involves some negative signs. So here I've got a geometric sequence, negative 4, 12, negative 36, positive 108. I want to find the common ratio. So I'm going to start by dividing the second term by the first. 12 divided by negative 4 is negative 3. And then I want to see if that's a common ratio. So I divide negative 36 by positive 12. That's also negative 3. And then 108 divided by negative 36, also negative 3. So I see my R value here is negative. One thing that creates in this sequence is a change in sign from term to term. And one way that we describe that is as an oscillating sequence. It goes back and forth between negative and positive. Well, let's also identify the first term. A sub 1 is negative 4. So again, I've got my explicit formula template now. Remember, that's a sub n equals the first term a sub 1 times the common ratio to the power of n minus 1. So I'm going to substitute in my first term. A sub 1 is -4, common ratio of -3. I'll put parentheses just to preserve those negatives, and then I'm going to fit the rest of the formula around it. A sub n is -4 times base -3 to the power of n minus 1. Here I'm looking for the 9th term. So again, I'm going to pick up a sub 9 and set that equal to my explicit formula, -4 times the growth rate -3 to the power of n. I'm going to substitute in 9. I'm looking for the 9th term, minus 1. So our a sub 9 is going to be -4. I should write what I say, -4, -3 to the power of 8. Again, we'll use the calculator to actually evaluate that number. And here in Desmos, we'll type -4 times -3 to the power of 8. And that gives us a very large number, -26,244. We'll head back to our note screen to finalize that product. Again, when we calculate, -26,244. So those two examples asked us to write an explicit formula. The next two ask us to record a recursive formula. So recall from our work with arithmetic sequences, a recursive formula defines each term according to the term that comes before it. That's what recursive means. It means going back to determine your present value. I need the two essential things still. I need my growth rate, and I also need to state what my first term is. So I can find the growth rate first, same way that we've been doing. I'm going to divide the second term by the first. 6 divided by 2 is 3. And then to see if that's common, I'll divide the next pair. 18 divided by 6 is 3. And similarly, 54 divided by 18 is 3. So my R value is 3. And really, all I need is a sub 1. That's going to be my first term 2. And then the formula for a recursive description of a geometric sequence. So it's recursive formula for geometric sequence. Is going to be given by this equation. It's going to be a sub n equals r times a sub n minus 1. Essentially, a geometric sequence says you take the previous term, multiply it by the common ratio, it'll give you your next term. So for us, for our recursive formula here, a sub n is going to be equal to my common ratio of 3 times the previous term, a sub n minus 1, for values of n that are greater than or equal to 2. So you do need to include that description of what my n values can be, so we don't get, say that we have n values less than 1. I also want to find a sub 11. So recall with the recursive formula, we don't have access to a certain term in the sequence. We only have access to the next term. So really what I'd need to do is just multiply and find 11 terms by multiplying by the common ratio of 3. So here on our screen, we can multiply 54 by 3. And that's going to give us 162. That's my 5th term. We got to get to our 11th term. So 162 times 3 is 486. 486 times 3 will give us 1,458. That's my 7th term. I'll keep going. 1,458 times 3 is going to give us 4,374. That's my 8th term. 4,374 times 3 is going to give us 13,000. So these numbers are growing very rapidly. It's exponential growth, you can see. 13,122. I've got 2 more terms. 13,122 times 3 is 39,366. 1 more term. 39,366 times 3 gives us our 11th term, 118,098. So definitely there's an advantage to having an explicit formula. You can see with the recursive formula, to get out to a term in the center of the sequence, it takes some time. It also introduces potential error. So it's good to note that there is an advantage to having the explicit formula. Well, we'll take a look at one final example. So here again, I have an oscillating sequence: 2, -4, +8, -16. So again, I'll start by finding common ratio. -4 divided by 2 is -2. 8 divided by -4 is also -2. So I'm checking to see if it's common. -16 divided by 8 is -2. So my R value is definitely -2. So if I'm going to write a recursive formula, I need to state my first term. A sub 1 is 2. And then for my formula, A sub n, it's going to be the growth rate, -2, times the previous term, A sub n minus 1. So that's my recursive formula. But as we saw, it really takes a lot to multiply out. So to find something like, in this case, A sub 10, the 10th term in the sequence, it really would behoove me to just write the explicit one and then use that to find A sub 10. So although we did find the recursive formula here, let's also find the explicit formula. So again, just to remind how that goes from our first 2 examples, A sub n is A sub 1 times the rate to the power of n minus 1. So if I'm looking for A sub 10, that's going to be equal to my first term, 2, times the common ratio, -2, to the power of 10 minus 1, or simply 2 times -2 to the power of 9. So again, I'm going to take that to the graphing calculator. Really just a scientific calculator would suffice. And we'll calculate here. So that's 2 times the common growth rate, -2, all to the power of 10 minus 1, which is 9. And that gives me a value of -1,024. A sub 10 equals -1,024. Thank you for joining for this investigation of writing explicit and recursive equations to represent geometric sequences, and using the explicit and recursive equations to predict one of the terms in the middle of the sequence. Thank you for joining again. See you soon.